Okay, and finally, for our last video relating to the section of the text on linearly independent sets, let's prove the following theorem, which is called the characterization of linearly dependent sets. So an indexed set S, which contains p different vectors, v1, v2, up to vp, where now we're going to assume that p is at least 2. So we have at least two vectors in this set. So such a set is going to be linearly dependent if and only if at least one of the vectors in this set is a linear combination of the others. And we proved this kind of informally at the very start. So let's take a look at this a little more formally down below. And so this is an if and only if statement. So that means for those that have taken Math 3000 or a class in math proof writing, we need to prove two things to prove an if and only if statement. I need to prove that if this set S is linearly dependent, then at least one of the vectors in S is a linear combination of the others. That's what we would call the forward direction. And then we would also need to prove the reverse direction, which is the other way, namely that if at least one of the vectors in S is a linear combination of the others, then that would imply that this set S is linearly dependent. So let's first consider the forward direction. So I'm going to assume that this set of p vectors is linearly dependent. And what I'm hoping to show is that at least one of these vectors in the set S is a linear combination of the others. So if we have this set S, we assume it's linearly dependent, then what that means by definition is that there exists weights C1, C2, C3, all the way up to Cp, where at least one of these C's, one of these weights is not 0, so that when we take this linear combination of C1 times vector 1 plus C2 times vector 2, all the way up to Cp times Vp, we are able to get the 0 vector. So in other words, we have a non-trivial solution to this vector equation. So let's just pick one of them to be not 0. I'll just choose an arbitrary C sub j weight is not equal to 0. So then this arbitrary term Cj Vj falls somewhere inside of this sum. And we can pull that to the other side. We can subtract Cj Vj from both sides, and that would give me minus Cj Vj is equal to the sum of all of the rest of the terms. And so that handles this step over here. And after we've subtracted Cj Vj from both sides, since we've assumed that one of these is not 0, we now divide both sides of the equation by minus Cj, which we can do since it's not 0. And this gives me Vj is equal to minus C1 over Cj times V1, minus C2 over Cj times V2, and so on. And this concludes the forward direction, since now we can see that this vector Vj that had the non-zero weight, it is a linear combination of the other vectors in the set. And let's informally consider the reverse direction of this proof. So for the reverse direction, we instead assume that one of the vectors in the set S is a linear combination of the others, and then we're going to try and prove, therefore, that the set S has to be linearly dependent. So I'll write the proof up here. So now we're going to assume that this vector, well, without any loss of generality, we'll say the first one, V1, is a linear combination of all of the other vectors. So it's some weight times V2 plus some weight A3 times vector V3, all the way up to weight AP times VP. So vector V, we're going to assume V1 is a linear combination of all of the other vectors in the set. And so let's consider the vector equation, which is C1 times V1 plus C2 times V2, all the way up to Cp times Vp equals the 0 vector. And we want to determine whether we have a non-trivial solution. So let's let C1 equal minus 1, and then we're going to let all of the other C's equal to the weight that we needed when we took their linear combination to get V1. So then if I pick this combination of C1 is equal to -1 and all of the other C's are going to equal the corresponding weight AI that we use to get V, well then this combination is going to get us the zero vector for sure, because each of these is going to undo each of these. So we get back the zero vector. We've just shown that a non-trivial solution exists, so therefore this set of vectors has to be linearly dependent, and that proves the reverse direction.